For ketones and aldehydes, let's start off with just synthesis. So remember, you will have multiple synthesis questions, and you might have a final product that you're trying to get to, and it's either a ketone or an aldehyde. And let's go over the different ways as to how you can create or form an aldehyde or a ketone. So the first way is going to be oxidation. A lot of these, by the way, are review. So we will review and go over certain ones that we have all throughout, like going over oxidation of alcohols or going from an alkyne to a ketone or an aldehyde and so on. But the first one is going to be a primary alcohol going to an aldehyde. And then we'll look at all the different oxidations of alcohols again. So remember that what we do is we have some sort of oxidizing agent, and we start off with a primary alcohol. And this oxidizing agent is then going to allow us to get to an aldehyde. If we were to continue with this and added another oxidizing agent to this aldehyde, then this would form a carboxylic acid. And remember, our oxidizing agent here could have been PCC going from a primary alcohol to an aldehyde. And then if we wanted to continue, this could have been the Jones reagent or chromic acid. And then, of course, remember that there are different oxidizing agents, specifically the strengths of them is going to be important, where our PCC isn't the strongest, but chromic acid and the Jones reagent would oxidize this. It would skip the step of going to an aldehyde, and it would instantly go from a primary alcohol to a carboxylic acid, since this oxidizing agent is relatively strong. We could also go from a secondary alcohol to a ketone, and then we would use a Grignard reagent to do this. So what we would start off with is we'd start off with a Grignard reagent, and then we'd add this to an aldehyde, and that would then form our secondary alcohol. Then from this secondary alcohol, we can oxidize this. So I'll use the chromic acid, in this case, reagent, and then that gives us our ketone. For example, we could have something like this. We'll start off with our aldehyde. Our Grignard reagent is here. And then this is an ether and acid. And then this combined will then give us our secondary alcohol. And then at this step, now we can oxidize this and get to our ketone. So just as an overview, what we talked about before with the oxidation of alcohols, remember that we said a primary can then be oxidized and get to our aldehyde. Do this again, oxidation step again, and then this gives us our carboxylic acid. Going from a secondary alcohol, we oxidize this. This then gives us our ketone. And lastly, if it's a tertiary alcohol, there will be no reaction. And then we know just the different types and different strengths of these oxidizing agents. We have chromic acid, which is going to be strong, and then it goes from a primary alcohol to a carboxylic acid instantly. It doesn't go to an aldehyde. Versus the Jones reagent, which would be the same exact thing because it is a strong oxidizing agent. But if we were given PCC, which is a weaker oxidizing agent, this does give us the aldehyde. So beware of that. If we wanted to go from a primary alcohol and we wanted to get to just an aldehyde, we would not use either one of these reagents. We would only use PCC. Now, if we started off with a secondary alcohol, if we use the chromic acid reagent, then this will give us a ketone. Same thing goes for the Jones reagent. And same thing also goes for PCC. So any one of these reagents is going to work from going from a secondary alcohol to a ketone. For example, if I started off with the primary alcohol, I would use PCC to then change this to an aldehyde. Next, if I had something like this, or if I even wanted to go backwards, where this ended up giving me part that's a ketone and another part that's a carboxylic acid, remember that with oxidizing this, if I were to kind of start off with the beginning portion here, well, even if you're going backwards, I know that what made this into a ketone? Well, this must have been a secondary alcohol. And then how did this get to be a carboxylic acid? Well, this was probably an aldehyde, and then it oxidized further. So that's one way you can go backwards or forwards in case you were given a synthesis question like this. The next type of synthesis that we'll look at is going from an alkene to a ketone. And this was that oxidative cleavage that we saw before. This was in the alkene reactions. So we used this reagent with heat, and then this would give us a ketone and a carboxylic acid. And then remember, all we're doing is we're cutting along the middle here between our double bond, and we're placing an oxygen on either side. And then we're pretty much like separating this apart. And we will go over the key again because it's not going to be exactly the same as we see here. This is a hydrogen, and this actually does give us a carboxylic acid and not this aldehyde. So if we were to look at that shortcut that we talked about previously, where this would give us, let's say if there was a single carbon at the end, this would give us carbon dioxide. If we had a primary carbon here, this would give us a carboxylic acid. That's why we have this one here, because this carbon only is connected to one other R group or one other carbon. So that's where we get our carboxylic acid. And then lastly, we get a ketone whenever this is a secondary carbon. So meaning this carbon between the double bond is attached to two other carbons. So that will give us our ketone, and that's where we get our products. Let's do an example of this. So I'm just going to cut along the middle here and do this same process. So remember what I'm doing is I'm just kind of chopping this down, putting an oxygen and an oxygen on either side. If I were to look here, I'd see that this carbon is by itself. It's a single carbon, so this is going to give me CO2. And then the last part here, well, this carbon is attached to one other carbon, so that's going to be primary. That's going to give me a carboxylic acid. So I wouldn't form a ketone in this case. Now, if I looked at another example, let's do the same idea here, where I'm going to chop this down. This gives me an oxygen on either side. Let's identify, looking at the shortcut again. Well, I'll look at this carbon and I see that this carbon is connected to two other carbons. That gives me a secondary, so I will have one ketone so far. Next, this carbon is connected to, I'm looking at the carbonyl carbon. This carbon is connected to one other carbon. That's primary. That gives me a carboxylic acid. So I will get a ketone and a carboxylic acid, which I do in this case. Remember, another way that we can do this that was similar to the oxidative cleavage was ozonolysis. We went from an alkene to either a ketone or an aldehyde. And remember, we didn't really worry about the overall mechanism of this. It was once again going back to the shortcuts that we spoke about with reduction, so this reagent, or oxidation with this reagent. So let's just start off with reduction again. And this is pretty much the same idea where I'm chopping this down along the double bond and I'm placing an oxygen on either side. And I'm going to look back at the key or that shortcut list that I had. Since I know this is reduction due to this reagent, I'm going to look and see, well, this carbon is a single carbon. So there has to be an aldehyde in this case instead of that carbon dioxide, since it is a different reagent. So, okay, that's an aldehyde. Next, I'm going to look here, and I'm going to see that this carbon is connected to one other carbon, making it a primary carbon, so I know that's also an aldehyde. So my products will be two aldehydes in this case. So this one, since there is no other R group, I'm just going to state that that was really formaldehyde, right? That H and H, two hydrogens. And then here, I'm still going to add that hydrogen right here by that carbonyl carbon, so this would have been my other product to the left of this. We'll do the same concept where I'm once again going to split this down the middle, put an oxygen, and see what my products would be. So identifying each carbon type. So this carbon here, this is attached to one and two other carbons. That's secondary. That will give me a ketone. This carbon here, I'm looking at one other carbon being attached. That's primary. So I'll get a ketone and an aldehyde. And it's going to look like this, where this part, if we see this part to the left, this is my ketone. And then to the right, this is my aldehyde where I just placed a hydrogen here by that carbonyl carbon. We'll do this again now for oxidation. So I'll split this down the middle. This is oxygen and oxygen on either side. Then I'm going to look at my shortcut and see what do I have as my products. So for this first one, I know that this carbon is secondary, we said. So secondary gives me a ketone. This carbon was a primary, so that carbon is primary since it's attached to one other carbon. So that's a carboxylic acid. So my products are going to be a ketone and a carboxylic acid, where this OH group just goes on that carbonyl carbon. Let's just keep flying through some more examples. This one was, once again, oxidative cleavage, where I can split this down the middle of the double bond, put an oxygen on either side, and then let's look at that shortcut list again and determine what we would have. So if it makes it easier to just kind of see this a little bit more enlarged. So this carbon here is a secondary carbon since it's attached to one carbon, two carbons, so that's a ketone. This carbon here is attached to one other carbon, so that's primary. So I will get a ketone and a carboxylic acid as my products, which is exactly what I see here. Moving on to a different type of synthesis, remember this is hydration. So what we're doing is we're starting off with an alkyne and we're going to make a ketone. So there are two different types of ways that we can do this. There's the acid catalyzed and the base catalyzed. So this is going back to alkyne reactions. And I'm going to start off with the acid catalyzed and see if I start off with an alkyne, I would apply this reagent since this is hydration. And this is just going to allow me to remove this triple bond and get to a carbonyl group here on one of the carbons, the one that's most substituted here, that would form our ketone. And then for our base catalyzed, we could also form an aldehyde in this case. So the first type, the acid catalyzed, is going to allow us to get to a ketone. Base catalyzed allows us to go from an alkyne to a aldehyde. And all we're doing is we're changing the bottom portion here, but where this was acid catalyzed since we have an acid, and then this is base catalyzed since we have that hydroxide group here. And all that's happening is instead of this carbon being the carbonyl group, this is now the new carbon that's attached to hydrogen is our carbonyl carbon. Another type that we went over was the hydroboration oxidation, where once again this followed that anti-Markovnikov's rule. So recall that we start off with an alkyne, we apply this reagent, or really anything with boron is going to be your giveaway here. And then remembering that your hydrogen is going to go to the most substituted carbon, and then the boron goes to the least substituted carbon. After that, so that was hydroboration. After that, we have oxidation. So we're going to go another step further. And this allows us to remove the boron. So that's what oxidation is doing. It's removing that boron. It now becomes an OH. And then finally, we remove that OH and then form that carbonyl group, which in this case, this would create a ketone, an aldehyde. This would create an aldehyde because we have a hydrogen here. If there was another R group here, then it would create a ketone. So let's do an example of this. If you'd like, you can pause the video and try this question out again just to refresh your memory. So let's just start off with what this would typically look like. So I know that I'm going to start off with hydroboration, where this is anti-Markovnikov's rule. I know that the boron goes to the least substituted carbon, which is going to be here, and the hydrogen goes to the most substituted carbon between that bond. So that would have been here. Next, I know oxidation is going to occur to then form that aldehyde. So this gets removed, and then we can think of it as this is our new carbonyl carbon. So that's where I see it here. Okay. So this gets removed, that becomes OH, then that OH removes, and then we know that's our aldehyde overall. If I were to see another example, so the previous examples that we were looking at was a terminal alkyne, so that triple bond was at the end. And now if we looked at something, hydration of an internal alkyne, meaning the alkyne is in the middle between two other R groups. Well, let's just see what the differences are there. First, I know I have to do hydroboration, so I'm going to rewrite this a little bit differently, where I'm going to see that there's two carbons here and here. Might be a little bit confusing if we don't draw it differently. And then, so let's just double check how many carbons we have. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that's fine. And then I know that this is going to form our ketones. The reason why it forms ketones and not any aldehydes is because this is in the middle. This is in the middle of two different R groups. If there was a terminal alkyne, which we saw previously with the hydrogen at the end, that would form an aldehyde because there is a hydrogen there available. In this case, there isn't, right? There's no other hydrogens here. There's only R groups. So that's how I know that ketones would form. So that's a great example. If you have a synthesis question where your product is only ketones and they ask you to start off with your starting material as an alkyne, well, what type of alkyne would I start off with? If there are aldehydes or there is an aldehyde, then I know there must have been a terminal alkyne. If there's only ketones as my products, then I know that an internal alkyne is possibly going to be my starting material. Okay, let's do another example here. This is an example of a terminal alkyne, so I already know that an aldehyde is most likely going to be my answer here. So I'll start off with hydroboration. So remember, just attaching the boron on the least substituted carbon, hydrogen goes to the most substituted. Now I'm going to do oxidation and form that aldehyde. So this removes, we then turn that into OH. OH is then going to leave, and then from there, I know that that's the location where I would have that carbonyl group. Let's do another example of hydration. So we have our alkyne again. We have, this is acid catalyzed, since we do have an acid below. Next, I'm going to see what happens. So first things first, if we were to go over this reaction again, this is going to allow us to form an enol. And then lastly, after we form that enol, I know that I'm applying that acid, and that's going to form that ketone in this case. Remember, this is in the alkyne reactions if you need a refresher of hydration overall, but we're just looking at what can form that ketone. Okay, so just going from an alkyne, using hydration, specifically acid catalyzed, would then form this ketone. Next, let's move on to Friedel-Crafts alkylation. So this is going back to those benzene reactions. So we can start off with the benzene ring and then form a ketone. So I'm going to start off with my benzene ring. Then I'm going to add that halide here, of course, with aluminum chloride. And then once I attach those on, all I'm doing is I'm kind of just attaching on that ketone. That's it, right? With alkylation, that was the one where we attached that ketone. Alkylation, remember, was where we attached an alkyl group to a benzene ring. So this is one way that we can form that ketone and attach that ketone onto the benzene ring. For example, we could have something like this, where this is most likely what it's going to look like. All I'm doing is just removing that chlorine, attaching onto the benzene ring, and we're done. So in the case that you were to see just this as a product, well, you know that if I have that benzene ring and I have that ketone, it's going to be Friedel-Crafts alkylation. Moving on to going from a benzene ring to an aldehyde. So this was another thing, part of the benzene reactions, where I can see if I had a benzene ring and I'm trying to get to an aldehyde instead of a ketone, well, I know that I would use this overall, all these reagents. Just remembering that this is unstable, that's why we can't attach that to the ring like alkylation previously. Instead, we have to use a completely different type of reaction, and this is the reaction that we would see with that. That just allows us to go from a benzene to an aldehyde instead of a ketone. For example, if we had something like this, just remember that all I'm doing is I'm attaching on an aldehyde. So it's going to look something like this. And I know that, of course, this still goes with the idea of para and ortho directors. So remember, what happens there is we have an electron donating group, which is that alkyl group, that methyl group, and I know that that's going to be ortho and para directing. So ortho positions are here and here, and that tells me what location I'm going to place the aldehyde in that case, which I have that here. So this represents one ortho location, and then this para, there's only one para location, so I know that I also can place the aldehyde here, so I have two possible products in this overall structure. So if you were given, like if we're going backwards now, if you were given products that showed a benzene ring and an aldehyde, and possibly even just showing like you had an aldehyde that is in the para and ortho position, plus you have that methyl group, then you know that there had to have been some sort of directors. So one, it should have been a benzene ring with a methyl group attached to it, because this is in the para position and this is in the ortho position if we were to look back to synthesis. Or even just the concept of if you have a benzene ring and an aldehyde attached onto it, remember that these are the reagents that we would have to use to get to that point. The next type of synthesis is going to be going from a carboxylic acid to a ketone. So we'll start off with the carboxylic acid, and then we have an R group attached to that lithium. And from here, all we're doing is we're then getting to a ketone. So it's going to look something like this. Starting off with that carboxylic acid, we have an R group attached to lithium. We then form this dianion, which we did here before. And then all we're doing is essentially just adding on an R group, okay? So this carbonyl group leaves or breaks, and then we now have oxygen attached to lithium, oxygen attached to lithium, because this hydrogen also left. And then now we're going to see that that R group attaches onto the carbon here. So from that step, we then form our ketone. So a quick little shortcut that we can see is just we have this being the same. Let's actually show that. So we have this portion of that carbonyl, or that carboxylic acid, is the same in our ketone. The only difference is that we're adding this R group. Okay, so this R group is what's changing. That's it. That's the only thing that's happening with this. Now, if we were going from a nitrile to a ketone, what happens is we start off with a nucleophilic attack where this is going to attach onto the carbon. These electrons will then go back to the nitrogen. By the way, we could have had either some sort of Grignard reagent, or we could have had this as another reagent in that case. We're then going to form an imine, and then the next step is to add acid, and that forms our ketone. So all that's happening is we're going from, and even kind of just looking at what we're attaching on again, this carbon and this R group are still part of that ketone. The only thing that's changing is, one, of course, we are forming that carbonyl group, and this R group, whatever we're attaching on, that attaches on to the ketone. So it can look something like this, where this goes, we start off with our nitrile, and then this is going to remain the same. This is our R group and that carbon, so this is the same. And then we now have our carbonyl group. We're attaching on this R group to that carbon, and it forms that ketone on that benzene ring. We could also do reduction by nitriles. So I can start off with the nitrile. Using this reagent, I can then form an aluminum complex. Using acid, I can then get to an aldehyde. So it's really the same sort of concept here, where I'm still going to have that R group and that carbon. So I'm still going to have this. And then that hydrogen is coming from this location. And that's all. So this would form an aldehyde. Our previous concept of going from nitrile to a ketone, that was a little bit different since we use different reagents. We use Grignard reagents in that case. Let's look at an example of reduction of nitriles. So we could also use these different types of reagents. That's also common. We could, by the way, what you can do is you can start off with an alkyl halide. This allows us to get to a nitrile. Once we have that nitrile, we can then use this as both of our reagents. And then from there, that allows us to get to an aldehyde. That CHO just means that it is an aldehyde. That's accounting for this carbon, this hydrogen, and this oxygen. Another type is going from an acid chloride to an aldehyde. We would literally start with an acid chloride, any one of these reagents, either the top or the bottom here. And then from there, I would then form an aldehyde. So all you're doing is essentially removing this chloride and changing it to a hydrogen. It would look something like this, where we have this acid chloride. I know it has a rather large R group, but at this step, I can then just apply one of these reagents, and then I know the only thing that's changing is this chlorine, and it's changing to a hydrogen. Next, I could also go from an acid chloride again to a ketone, and I would start off with an acid chloride. I would then use this reagent, so two different R groups, remember going over something like this. And then from this step, I would then just form a ketone. So once again, all I'm doing is I'm removing this chlorine and I'm replacing it with just one of these R groups, which is here. For example, I could have something like this, where I start off with that acid chloride. I then have my organocuprate. And then once I do that, all I'm doing is I'm adding just one of these. I know there's two, but I'm only adding one of the R groups and replacing it in that location where that chlorine was, because this will leave and this would attack on. This is now my new ketone. Next synthesis allows us to go from an ester to an aldehyde. So I would start off with our ester, and then at this step I would apply this reagent. It is going to be under these types of conditions for temperature. We then form our aluminum complex, add water, and we form our aldehyde. Now, know that I'm not going over any mechanisms in this case because it's really not necessary. All I want you to know is that what type of reagents we would use to then allow us to go from an ester to an aldehyde. So I know that this is going to leave and this is just replaced with hydrogen. That's it, okay? So that's all that's happening there. For example, we could have something like this where we have our ester, we then have this as our reagent, so it could either be all of this with water, or it could look something like this. And then I know all that's changing is that OR group is going away and it's now just being replaced with hydrogen. So now we have our aldehyde. All right, so now that we did a review on just how to make a ketone and an aldehyde, let's get into the different reactions that we're going to see. So the first one is something known as nucleophilic addition, where all that's happening, the first thing we have is that, in this case, a ketone, but I want you to think of this as just some sort of generic carbonyl compound. So it's a compound that has a carbonyl group. Now, nucleophilic attack is going to take place where the nucleophile attacks that carbonyl carbon, and then this double bond is then going to break. And once that double bond breaks, these electrons go onto the oxygen, now making it an alk oxide ion. And at that point, we're now going to introduce an acid. So we have some sort of acid here, and I know that the electrons are going to take that proton. So we're going to protonate, and then this nucleophile is then going to be on its own. And then we form our product. So we attached on whatever nucleophile we have. So that attached to the carbon that was part of the carbonyl group, and then the oxygen then became an alcohol group. And then from there, we also have our nucleophile as a byproduct there. Now, there are going to be two different types. There's going to be one that's going to be under acidic conditions and another that's under basic conditions. Something to note, just looking at the different strengths between aldehydes and ketones. So aldehydes tend to be more reactive than ketones. And the reason for this is due to electronegativity. So let's just look at this ketone. We see that this oxygen is the most electronegative atom. However, since we have multiple R groups or alkyl groups, I know that this is going to make it a bit less electronegative. And then if we were to do nucleophilic addition here, this is going to be more crowded on our alk oxide ion because there are multiple R groups in this case. And then, of course, our product, once again, would be more crowded. Now, however, for an aldehyde, what we're going to see is this is going to be more electronegative because we no longer have as many R groups. So it does depend on how many R groups there are. And then that's pretty much the reason why an aldehyde is always going to be more reactive than a ketone, because it is going to be more electronegative. And our alk oxide ion is going to be less crowded overall. Let's start off with just acidic conditions for nucleophilic addition. So the first step is to protonate. So what we have to do here is we have our weak nucleophile, so that's going to be this oxygen. Looking at the electrons, that's going to remove a proton from our acid, and then at this step, we're going to get an activated carbonyl compound. So we have that activated carbonyl compound. After that, step 2 is our weak nucleophile is then going to attack the activated carbonyl carbon. So that's going to attack here, and then we get our final product. So the concept here is still that the nucleophile is going to attach to the carbon that was part of the carbonyl group, okay? So in this case, I know that the nucleophile overall has to be attached to this carbon, and then the double bond then breaks and just forms that alcohol. Now, under basic conditions, the first step is that nucleophilic attack. So a strong nucleophile will attack. So that was one of the main differences. So for an acidic conditions, under acidic conditions, we will have a weak nucleophile. And then for basic conditions, we have a strong nucleophile. So a strong nucleophile will attack the carbonyl carbon, and then it forms that alk oxide ion. However, for our acidic condition, it did not form that alk oxide ion. It instead just activated the carbonyl group. Next, we're going to protonate. So protonation occurs, and then we grab that hydrogen, this nucleophile goes away, and we formed our product. So really, it's just a different way as to how we're approaching this, and it's just different conditions. One is in acid, one is in base, but we will still get the same sort of product. Continuing on with our ketone and aldehyde reactions. So the next one is going to be going from a ketone as our starting material and ending with an alcohol. So I would start off with our ketone. Now I'm going to have some sort of Grignard reagent here where the metal or M is represented by one of these. And then next, I would then get to my alk oxide ion, add acid, and that forms that alcohol. Let's just look at how this is going to form. So I'm going to start off with just forming the Grignard reagent. So the formation of the Grignard reagent, remember that starts off with an alkyl halide. I then add magnesium, and this solution is an ether, and then this would form that Grignard reagent. Next, the Grignard reagent, now that it's ready, I'm going to allow that to attack the carbonyl compound. So that's going to attack the carbonyl carbon, and that's going to attach on. And then, so that R group attaches on, as we see here, that R prime and R prime. And then these electrons are going to go back to the oxygen, forming that alk oxide. And then next step is to form that alcohol by adding water. either water or acid. So I'm going to have that alk oxide that's going to protonate. So it grabs a hydrogen. These electrons go back onto the oxygen. That OH is then going to combine with this portion, that part of the metal. And then, of course, the main thing that we want to focus on is just how that alcohol came to be. And that's how it becomes. It allows us to go from an alk oxide, protonate, and that's how our alcohol group gets made. Remember, with Grignard reagents, what we could also see is we have formaldehyde. If we add that Grignard reagent plus acid or water, that's going to give us a primary alcohol. If we started off with an aldehyde and once again applied Grignard reagents, that gives us a secondary alcohol. And then starting off with a ketone, this will give us a tertiary alcohol. So if you'd like to practice this, we have done some of this before. So if you want to pause the video, try this question out, go ahead. So if we were to draw out the mechanism here, what's going to happen is that we're going to start off with our Grignard reagent. That's going to attack the carbonyl group, and then the electrons will go back onto the oxygen. This is going to form that alk oxide. That's going to form our alk oxide, and of course, this is our methyl group that we attached on here. So from that step, this is going to protonate and then form that alcohol, and now we have a tertiary alcohol. And then nothing happens to this alkene. That's going to remain the same all throughout. Now let's look at reduction. So remember, this is going kind of like backwards, where we go from an aldehyde or a ketone to an alcohol. So we can now start off with an aldehyde, and then this is our reducing agent. I can then get that to be a primary alcohol. If I had a ketone and I apply the same reducing reagent, that's actually going to give me a secondary alcohol. And then, of course, remember that if instead of hydrogen there, now we have reduction using deuterium. And the only difference is that sometimes you might actually see that they place D on that alcohol. So if that's the case, then I know this reagent is telling me it's going to be deuterium instead of hydrogen. But it's the same result. An aldehyde with this reagent, even with deuterium, is still going to give me a primary alcohol, and a ketone is still going to give me a secondary alcohol. Another form of reduction, remember, was this type, that rainy nickel and with hydrogen 2, so H2. So all that's happening is we're going from a ketone to an alcohol. And that was really the main idea here, where I'm reducing this from a ketone using this reagent and going to a secondary alcohol. Another form of reduction was the Clemmensen reduction. I would start off with the benzene ring, and then I'd have my alkyl halide. And then, of course, I'd have aluminum chloride and water. And all that's happening is that this is allowing me to go attach on this ketone. So we attached on the ketone. There's one more step here. Remember that this first step was just the Friedel-Crafts acylation. And then I would have this reagent with acid. And then this allows me to remove that carbonyl group to then form an alkane. So this is just another way that we can reduce. So it starts off as a benzene ring, but we do have kind of that carbonyl group. From that step, maybe they might give you something like this. This is like their first step. So you started off with a ketone attached to the benzene ring, and you wanted to get it down to an alkane. This is the additional step that we would see, just that zinc with mercury and acid. So this is just another example. You would possibly be given something just like this step. If you were given a synthesis question, you might go from, like, this is your product, and they're giving you your starting material as a benzene ring, and you know that the first step is going to be that Friedel-Crafts acylation, and then the last step is that Clemmensen reduction part. Another type of reaction allows us to go from a ketone or an aldehyde to an alkane. So we'd start off with a ketone. Now we're applying this hydrazine. So this is hydrazine. And then what that makes is then a hydrazone. So all that happens is this oxygen is going to leave, and then we're attaching on these two nitrogens on top. From there, we're going to add a base and heat, and that allows us to reduce this down to an alkane. For example, we could have something like this, where we have a ketone on a cyclic ring. We then apply that hydrazine and our base and our heat, and that just completely cleaves this off and removes that carbonyl group, just giving us that cyclic ring. So let's look at what's happening here. So first things first is that a proton is going to transfer from a nitrogen to a carbon. So what I already did, the step that I went to was where it was a hydrazone. Okay, so this is a hydrazone. Just going back real quick. This started off as a ketone. it then got attached to a hydrazine. Now it's a hydrazone, and now this is the step that I'm worried about. So what's going to happen with this is that we're going to protonate here. So this oxygen is going to grab the hydrogen. These electrons then go onto the nitrogen. And then at that step, we're going to have some resonance here. So this is stabilized. Then we're going to have water, and water is then going to, well, protonation is going to happen here. Carbon is going to remove one of those hydrogens. It's going to look something like this, where hydrogen is now attached to that carbon. And then once again, we're going to remove a second proton from the nitrogen. So removing this proton. And then, by the way, but with this men up top, the proton's transferring from nitrogen to carbon. All it means is that one of these proton leaves, right? We only have one proton here. And then the next thing is that that proton basically just gets attached to this carbon. And then we're going to do something like that again, where this proton is now going to be removed by that base. And we no longer have that. Next, we're going to lose this N2. And then protonation is going to occur. So this is off to the side now. It's just in the solution, or it's our byproduct. And then now we have carbon that's going to grab a hydrogen. So it's protonation at this step. And then finally, we just formed that alkane. And we have that base and these two nitrogens attached. That's also going to be off to the side. So if you feel okay to try this out, I'm going to say try both of these questions out, and then we'll go over it together. So there's no need to do the mechanism here. Remember, this reagent with zinc mercury was an acid, was the one that the Clemmensen reduction, where we first started off to even get this starting material. We started off with Friedel-Crafts acylation. Then we reduced this down. So all we have to do is remove this carbonyl group, and you're done. Remove this. This now is an alkane, and that's the only thing we had to do. For this next one, this is a hydrazine, and then this is a ketone. So I know I have to form, I know that this is going to still give me that alkane. So it's this concept again, where all I'm doing is I'm essentially, if you were to look at the shortcut here, I'm going from that carbonyl group to two hydrogens. So I'm removing that carbonyl group again, so I can cleave this off and see I'm done. It just gives me an alkane. So start to get familiar with that and just how quickly you can do these questions, because a lot of times you aren't going to be asked to write the mechanism for a lot of these types of questions. It's just going to be, what's the product? And all you have to do is cleave this off, so remove that carbonyl group, and you form an alkane. The next type of reaction is a Wittig reaction, where we're going to start off with an ylide plus an aldehyde or a ketone, and that's going to form an alkene. So the only thing that's really happening is that we're kind of like pushing these two together, where our ylide is always the one with phosphorus. I'm going to see that the portion of this ylide is going to be carbon and this carbon, and then our R group and our hydrogen, which is on the left. And then next, whatever ketone or aldehyde that we have here, that's going to be on the right side. So we're literally just taking these two and combining them. And we no longer have that carbonyl carbon, or that oxygen. That's now going to be attached to that phosphorus here. So this is the main alkene or product that we see overall in this reaction. For example, I could have something like this, where I have my ylide again. Now I do have an R group, I have a methyl group, and then I have this cyclic ring. So I do have a ketone in this case. And all that's happening is this part, another way we can look at it, is this oxygen is going away, and it's being replaced with whatever was on our ylide, and then now that's put together. So that's one concept here, where this oxygen goes away, and I'm just replacing it with what I have circled here. And I know it's a little bit flipped around, but either way, it would have been correct. So just to look at this further, the ylide is going to attack the carbonyl carbon, and then it's going to form this state, just because it is attaching on. And then next, we will see, this is our next reaction. Step 2 is then to form a ring. So this oxygen is going to form a ring with phosphorus, so it's going to look something like this. Then our ring is going to collapse, and that's how we break these two apart and form our alkene and this. There might be a case where you have to figure out how they formed the ylide, and how that's going to take place is we're going to start off with an alkyl halide, but then we're going to have that phosphorus with 3 phenyl groups, and an SN2 reaction will occur. So this all happens in one step, where this is going to attack this carbon, our leaving group leaves, and that's how we formed the first part. We're not done just yet. So that's how we formed that first part. We have bromine as our byproduct. And then the next step is going to be deprotonation with the strong base. So some sort of strong base here, so anything with OH. And I know that this is going to remove a proton, these electrons, and go onto here. And then now we have an ylide that is ready. So the main thing is that I know I didn't form a double bond. Instead, what I looked at was I just saw that this is going to now have a negative and positive charge, and it is going to be ready to react. So another little thing that you might see is that you will see this as your reagent as well. So in the case, if you ever need to form an ylide or do this whole Wittig reaction, you would start off with an alkyl halide, then add this phosphorus with the 3 phenols, form the ylide, then do the reaction of an ylide plus either a ketone or aldehyde, depending on whatever alkene you're trying to find. So what I want you to do is try 3 questions out. Pause the video now, and then just a note, try not to do the mechanism. Just try to put them together, like we said before, with like the shortcuts and predict the products. So for this first one, all we're doing is we're replacing this oxygen with whatever R group and carbon was on that ylide. So I would then place this carbon here instead, and this oxygen now goes here. So that's really it. This is going to remain the same. We have 2 methyl groups from that ketone now on that alkene, and then this phenyl group and carbon will remain, will actually attach on to this other carbon. So that would be it. So these 2 are essentially just swapping places. Same thing goes for number 2. So I'm going to replace this oxygen with this group, and that's now going to be my new alkene. And oxygen is now going to be double bonded to this phosphorus. So these should be pretty quick, pretty simple to just kind of smush them together and see. Let's look at the same thing here, where I know that this one's a little bit longer, so I did count or number everything, where this oxygen attached to this carbon. If you're not seeing that just yet, what we could do is counting, okay? So we can count the carbons here. This is 1, 2, 3, and this is carbon 4. So carbon 1 and 4 will attach, and that becomes that double bond. And then this remained the exact same since we see that 1, 2, 3 carbon. So if you do have some cases that are a lot longer and a lot more complicated, I do recommend counting or numbering the carbons and then seeing how they're going to connect and making sure that everything connects, accordingly. Now, if you were asked to go backwards, this is a common question, just asking to find the reactants or starting materials from this product. So what I would start off with doing is just splitting this apart. So I would start splitting this in half in the middle where that double bond is. So I know that one side is going to be my ylide, the other side is going to be either my ketone or my aldehyde. And there are 2 possibilities in this case. Well, I know that if I were to split this down the middle, I'm going to look here and see this has 2 R groups. So that could have been a ketone. So I could have started with a ketone, and this is my ylide, where that has the ethyl group and the hydrogen. Or I could have switched this up and seen that maybe this is going to be my ylide and this is going to be my aldehyde in this case, since this has a hydrogen. So I could have swapped it and had it look like this, where my ylide now has the 2 R groups or the 2 methyls, and the aldehyde and now I have an aldehyde in this case. So those are just 2 different possibilities that we could see. The next type of reaction is hydration. So what we're doing is we're forming a hydrate. And this is what a hydrate looks like, or kind of think of it like a diol. We have 2 different alcohol groups, but we start off with either a ketone or an aldehyde. We then add water and HCN, and that will form our hydrate. And the main focus that I want you to look at is this carbonyl group is just changing to a diol or to 2 alcohol groups. So the only thing that's changing is this carbonyl group or this double bonded oxygen is changing to 2 alcohol groups. But let's look at the overall process. The first step is going to be protonation of that carbonyl group. So that oxygen is going to grab the hydrogen in the acid, and that's going to then protonate this oxygen. Next is the addition of water. Remember, water just came from that acid since we removed a proton that now has 3 hydrogens, so H2O. That water is then going to attach on, and then this has to make room for it because there's too many bonds on our carbon, so those electrons are going to go onto the oxygen. Now that we have that, this is no longer charged. We attach that water. What happens next is deprotonation. So another water molecule is then going to deprotonate this water. These electrons go back onto this oxygen, and that's how we added those two alcohol groups, forming that hydrate. Now, that was in acid, okay? So there could have been hydration using acid or basic conditions or in base. So now what we would do first, if this was in base, this is going to start off with the addition of hydroxide. So I would see I have hydroxide, that's going to attach onto carbon. These electrons are going to make room for that carbon to attach onto the oxygen or OH. And then these electrons go onto oxygen, and it's going to look something like this, where we formed that alkyl oxide ion. Next, protonation will take place, where oxygen is going to remove a hydrogen. These electrons then move back. That's how we get our byproduct of OH, and we formed that hydrate. So either way, they will form hydrates overall, whether it's an acid or in base. Something to note is just the strength of that hydrate. So the more alkyl groups, the more stable, but that would just mean that our ketone is more stable. It doesn't mean that our hydrate is as stable. So it's kind of the opposite thinking there, where if there are more alkyl groups, that actually means that our hydrate is going to be less stable. Okay, that's the main takeaway here. Aldehydes are more likely than ketones to form hydrates. The main thought there was just aldehydes, remember, were more reactive than ketones. So those are going to form better hydrates than ketones. So aldehydes form better hydrates, ketones do not. Next is the formation of cyanohydrin, which looks like this. It does have an alcohol group, and it also has a CN. This is really similar to what we just saw. The only difference now is just instead of two alcohol groups, there's only one, and we now have a nitrile attached. So we're going from either a ketone or an aldehyde. We're adding HCN, and that forms that cyanohydrin. For example, if I had an aldehyde, I added that HCN. All I'm doing is I'm removing this carbonyl group, and I'm changing that to OH and CN. Let's look at the overall process of this. So cyanide is going to add to the carbonyl carbon. These electrons then make room for that, so they go onto the oxygen, forming that alkyl oxide. And then next, I will add that HCN. So protonation will then give us that cyanohydrin. So then oxygen grabs that hydrogen to protonation. These electrons then go onto the carbon. And then all we did was we pretty much just attached on that CN and we formed that OH by protonation. So first step just allowed us to get that CN. Second step of protonation allowed us to get that alcohol end. If you'd like to try out this question, please do. Let's look at the overall mechanism. So step one is just our nucleophile. That strong nucleophile is going to attack that carbonyl carbon. These electrons then go onto oxygen to form our alkyl oxide. Next, we want to protonate to then form that alcohol group. So this is going to take place, protonation. So oxygen grabs that hydrogen. These electrons go into carbon. That's our byproduct. And we formed that cyanohydrin. Moving on to the formation of imines. So I can start off once again with either a ketone or an aldehyde. And then I'm going to add a primary amine with acid. That's going to form our imine. And then, of course, our byproduct would then be water. So the main thing that we're doing here, if you note, this is changing. That oxygen is being replaced with whatever primary amine that we have. So that nitrogen and that R group are attaching here. We no longer have that oxygen. That oxygen is just going towards this addition of water, this addition of water, essentially. It could look something like this, where we start off with our ketone in this case, and we add that primary amine. We have H plus in our solution, and then these two are basically replacing. So oxygen goes away. We now have that nitrogen attaching on with that R group or methyl group in this case. The whole process of this is going to be, we start off with our carbonyl compound, and then this forms this stabilized cation. From there, we're going to have our primary amine, and that's going to attack that carbon. Then we're going to have the addition of our overall amine. So let me go back to this first step. I realized I didn't mention this part. Protonation is our first step here, which is going to allow us to get to this step here of that protonation. And then from there, we're going to add that amine to that carbon, which we have here. Next, we're going to see that we have, we're going to have also the addition of water that's going to deprotonate this hydrogen. and then these electrons go on to nitrogen to make this neutral. Now we're at this step, so after we deprotonated, we have this. I'm going to continue on. There's several more steps. So next step is just protonation of that alcohol group. So we're going to grab that hydrogen. Now that we have water here, right, H2O, now we're going to lose this water since that is a good leaving group. So that detaches. Next, we have a minor and major here. So this is still being stabilized by resonance. But finally, we're going to deprotonate this with water that removes the hydrogen, electrons go on to nitrogen, and we finally formed that imine. Typically, you aren't asked to build this or draw out the mechanism, luckily. Just understanding how everything is changing is going to be beneficial. So what I want you to do without drawing the mechanism, just figure out what the products would be for these 3 questions. So remember, all that we're doing is we're replacing this oxygen with whatever we attached on. So in this case, our primary amine is really just ammonia, and that's going to attach on here. So NH is going to attach on instead of the oxygen, and this is what we would have. And of course, our byproduct would have been water. For number 2, all we're doing is we're replacing that oxygen with this benzene ring and nitrogen. So nitrogen is going to attach here. And that comes along with that R group. So that's it. That's all I want you to see is how these 2 are combining. Lastly, with 3, we're going to replace this oxygen with this nitrogen and methyl group, and it's going to look like this. So that's how we're forming that imine. Next is the formation of oximines and hydrazones. So the first thing I'm going to do is I'm going to add either a ketone or an aldehyde, and I have this hydroxylamine. And then I have acid, and then we're going to form this. Now, the main thing that I want you to see how this is all forming is as follows. So this oxygen is going to go away, and then this is going to be replaced with this entire portion, as we see here. So these 2 are replacing each other, where the nitrogen, well, only one nitrogen is going here on the oxygen, and then I have that OH group here. So that's what we're forming. I could have also formed a hydrazone where now this oxygen is just being replaced with this nitrogen, and kind of think of it as this is like the cutting point here where this nitrogen and beyond are attaching onto this location. And that's how we form that hydrazone. So another thing that we can look at is there's several different things that can attach on or different possibilities with forming this. So this is just some sort of generic reaction where I can see that I'm going to say Z can be any one of these, okay? So it could be hydrogen, it could be a phenyl, the OH group, or NH2, and so on, and it could be all of this, all right? So that just means that this is what would be replaced. So we're still adding the nitrogen that's attached here and replacing it with the oxygen, and then whatever that Z would be, that's what we replace. So if this was a hydrogen, now this would be a hydrogen. This was a phenyl group, now this would be a phenyl group, and so on. If this was an alcohol group, this is now an alcohol group. So that being said, go ahead and try some of these questions out. So for this first one, all that's going to happen is that we're going to see that this is going to be replaced with the nitrogen and that OH group. So remember that Z and that Z. So this nitrogen is going to be replaced here with that oxygen, and that's all we did. So I just had nitrogen and OH here. For number 2, all I'm doing is I'm removing this oxygen and replacing it with this nitrogen group. So I know that this is the new attachment here where we do have 2 nitrogens. So this is that first nitrogen here. And then next, this nitrogen is the one in yellow that we're attaching on. So that's that Z that we were discussing. Continuing on with number 3. So what's going to happen is that this oxygen is going to go away. This nitrogen is then going to attach on here, and we have that N and NH2. Remember, the whole concept is just us having that Z and that Z here that we mentioned before, where this is essentially just going to, this one is going to essentially attach on, and this is being represented as that Z. Moving on to another type of reaction where we are forming acetals. So I know that this is what an acetal would look like, where I do have that carbon, and it is connected to an oxygen and an R group, an oxygen and an R group. Okay, so all I'm doing here is I'm adding a ketone and an aldehyde, and I have 2 alcohols and acid. So it's really the same sort of concept where I'm removing this carbonyl group, and I'm now replacing it with these 2 OR groups. And for example, it could look something like this, where I have that alcohol group and I see that, or two alcohols in this case, or a diol, and I see that this is going to go away, and then this is going to form something like this, and we will go over what this would look like essentially, but it is that OR group, where that OR group in this case is the CH2, which this is a CH2, and this is also a CH2. That's how that's attaching on. Let's also look at the formation of hemiacetals and how this could possibly work. So I would start off with the ketone, and I'd start off with protonating that ketone. Now that I protonated that ketone and it's resonance stabilized, then I'm going to add alcohol. So adding alcohol to that carbon, and then now that's going to give us something like this. Right, so we just added that alcohol group. Now we're going to deprotonate this with another addition of alcohol. So removing that hydrogen, these electrons go onto the oxygen, and it's going to form that hemiacetal. So a hemiacetal, the only difference is that we no longer have two OR groups. We only have one, and the other one is an alcohol group. Following that, I can continue on with that hemiacetal, and I can do protonation. So I'll grab that hydrogen. From there, that forms water. Water is a good leaving group, so it will leave. Now I have that OR group that is resonance stabilized, and I have water as my byproduct. Next, I'm going to add an addition of alcohol again, and that attaches onto that carbocation, or where it was. Next, this is how, from this step, I attached on that alcohol group. Deprotonation is then going to occur, removing that hydrogen. And then finally, that's how I get that acetal, so I can go from a hemiacetal to an acetal by doing this whole process. And remember the difference here, hemiacetal had an OH and an OR, while acetal only has, it doesn't have an OH, it has two OR groups. Moving on to protecting groups. So something to know is that acetals can be made from either ketones or aldehydes. But the issue there is that they can actually convert back to the parent carbonyl compound. So they can convert back and forth, which doesn't really make for the best product if you just want it to stay like that. So protecting groups are the answer here. That's literally kind of says what it seems like it would say. It protects or even prevents that from happening. It prevents the reaction to go back to the starting material. So a protecting group prevents ketones and aldehydes from reacting with strong bases and nucleophiles. So the concept here is, let's say we had something like this where I had my ketone, and here I see that these two groups are actually not going to want to be compatible with each other, or they aren't compatible with each other. Where I have that aldehyde and I have that Grignard reagent end. Well, this wouldn't work, okay? So because this wouldn't work and this wouldn't carry on the main compound or reaction that I want it to, this wouldn't happen, and it wouldn't form my target compound, which is this, then I have to do something different. I have to add something that is known as a protecting group. So if I started off with that aldehyde, as I mentioned, and I no longer have that Grignard reagent, well, what I would do is I would have something like this where I do have that aldehyde and I do have now just bromine, not magnesium bromide, and I added alcohol, so a diol in this case, and acid. Well, this would form that protecting group. So sometimes they call it a masked aldehyde. This is really just the formation of a protecting group so that this doesn't react with anything else. And essentially what's happening is if the aldehyde is protected as an acetal, it is unreactive towards the Grignard reagent. So it's not going to react with itself. And that masked aldehyde, or that protecting group, will then be converted to the Grignard reagent, and now it's able to react with the ketone. So it just allows us to proceed with the reaction without worrying that this is going to try to be converted back to the parent carbonyl group. Okay, so we would then react this, by the way, with magnesium ether to then form that Grignard reagent. Now this is what it should have looked like instead of having that carbonyl carbon in this case. So this reaction would work. So now that we have that protecting group attached, these two would react, and we would get that target compound that we wanted initially. Next reaction, or the last reaction here, is going from an aldehyde to a carboxylic acid. This is oxidation. So I could do something like this where we've talked about oxidation before. We actually seen this before as well, where I can start off with an aldehyde, use an oxidizing agent, and this allows me to get to a carboxylic acid. So the reagents that we can see, remember, are the chromic acid, and this just once again goes from an aldehyde to a carboxylic acid, or I could use this. So this is another oxidizing agent that I can possibly use, and once again, that just allows me to go from an aldehyde to a carboxylic acid without affecting that alkene.